Okay, so thank you to come here, and I will also thank Ahmed for the kind invitation to present the work that we are carrying out at the Catalan Institute of Nanoscience and Nanotechnology in Spain. So the talk is going to devote to present our research on spin orbit proximity effects in van der Waals heterostructures. So this is one of the main slides of the talk. So I would like to highlight that this work has been carried out thanks to the excellent team that we had in the group. So I would like to highlight the student, the PhD student, Antonio, the postdoc Williams, and of course Sergio, that is leading the group. And I will also like to thank the theoretical support that from the group of Stefan Roche at the ICN2 and especially Jose Garcia. So this is the outline of my talk. So I will try to give a brief overview on proximity effects on van der Waals materials. I will also show you spin anisotropy experiments that induced by proximity-induced spin orbit coupling. And so what I will show you here is that by attaching together graphene with high spin orbit coupling material like transition metals like alkylenides, you can strongly modify the spin dynamics in the system. And finally, I will show you some spin to charge interconversion experiments, and in particular how we can generate the spin Hall and spin galvanic effects in graphene, and how this figure of merit that measure how efficient is this spin to charge interconversion can be strongly improved when you work with these van der Waals materials and you compare with other high spin orbit conventional high spin orbit coupling materials. And if I have time, I hope that I will have time, I will show you some other experiments that are very recently related to spin to charge interconversion with transition metals like alkylenides with reduced crystal symmetry. Okay, so another way to give you a flavor about the topic of the talk is here. So it's the design of artificial material by proximity effects and some spintronic applications. So there are two keywords here. So one is artificial materials and the other one is proximity effects. So what we mean by artificial materials, so we mean that with this, so we work with van der Waals heterostructures that are made of different two-dimensional materials. So here you have an example of the most studied two-dimensional materials that you have. So you have it's a very rich family of material platform. So you have insulators like hexagonal boron nitride, you have semi-metals, typically graphene, you have high spin orbit coupling material like transition metal like alkylenides, you have also some exams here, black phosphorus, Ahmed is an expert here in black phosphorus. And well, here you can see, so there are more than, so there are some reports, some collected databases, so you can see that this is huge. So you can have, so in these databases you have more than 40,000 entries, and indeed there are some algorithms to see how many two-dimensional materials can be stable, and you have this gigantic number. So so this platform is very rich, so you can play, you have a lot of possibilities, and this is a very famous image that illustrates what we do. So we basically combine different two-dimensional materials, and we just take properties. Just for instance, we can combine the graphene that is excellent from the point of view for spin transport. We can combine with high spin orbit coupling material like transition metal alkylenides, or you can also use some dielectrics to create barriers or to protect the devices. So there are two ways of doing these stackings. So a quick way to do that is by mechanical exfoliation of these materials, and then you stack in a controlled way. And there is a second way to do that, that is by physical deposition, layer by layer, in a controlled way. So we do both in our group. But what I will show you here today is these results on this way of stacking. So again here, so what these are proximity effects. So the take-home message is that a proximity effect. So when you combine these materials in these complex vertical heterostructures, the final result of this guy is not equal to the sum of these individual components. Okay, so you can imprint properties that are not in the pristine form. So the most typical example is in parameters like the spin diffusion length, the spin diffusion time, the spin diffusion constant. So now the point is we want to, so this technique is sensitive to the spin lifetimes when the spins are precessing in plane. But what's happened if the spins are precessing out of plane? So we have to develop, so there is an evident configuration, so you can apply the magnetic field along the spin channel direction. So in this case, you have spins that are precessing out of plane, but this has some technical disadvantages. So what we developed in the group a few years back is an oblique technique in which we apply the magnetic field at specific angles respect to the easy axis of the ferromagnet. So if the anisotropy is larger than 1, you have these lines here that are above, or if it's smaller than 1, you have this representation will be below this line. Okay, so then this is what we do. In this, so this is a picture of one device, and you can distinguish here two regions. So the first one is this. So before that, so we combine metal. So you have metal electrodes here. So these guys and these guys are metals, and then we put these spin-sensitive electrodes to inject and detect the spins. And you can distinguish here two regions. One that is a channel that is pristine graphene, so regular graphene, and then we have a second region in which we partially cover graphene with a transition metal decacoinate. In this case, it's tungsten disulfide. We did the same with molybdenum disulfide. So I will just show you that we observe exactly the same. So all the results that I will show you here is with tungsten disulfide. So if you go to the regular graphene, and you just carry out these experiments. So, okay, let's first measure qualitatively. So remember that this is not it's technically not, it will give you not the quantity, but it will give you the flavor if it's isotropic or anisotropic. So if we apply the magnetic field in this region, in the device with the magnetic field out of plane, and we measure in this region, when we apply the magnetic field out of plane, we have this signal, this is blue. Okay. And if we apply the magnetic field along the channel and the spins start to precess out of plane, we have exactly the same signal. So this means that you have an isotropic system. There is no difference in the spin lifetimes between one configuration or the other. But then blazingly, when we went here to this region, we observed that the dynamics is completely different. Okay? So when the spins are precessing in plane, the signal is strongly reduced. You see that when they start to precess out of plane, so they start here with a minimum signal, but then they start to acquire a magnitude. And they reach a maximum peak when the spins are exactly pointing out of plane. So, in other words, what is happening here is that we have a spin filter. So if the spins are in the plane, they are blocked by this bilayer, by this region, while if the spins are exactly pointing out of plane, they can pass through this. So we can block spins depending on how they are oriented in the system. And this is the representation. So this is remember in the cosinus square representation, if we plot how are these curves, the spin signal as a function of this cosinus square of the oblique magnetic field. So here you have what we measure for regular graphene. So this is the experimental points that drops within the uncertainty of the experiment in a straight line, so it's isotropic, while this strong deviation is a clear indication that we have spin anisotropic dynamics. And from these curves, we can extract what are the spin lifetimes for spins precessing in plane or out of plane. You see that there is an order of magnitude of difference that is significant. So now the question is, okay, what is the mechanisms, how the spins relax in this system? So this is something that was predicted by, well, indeed was not predicted by the group of Stefan Roth. So they asked themselves, okay, so what's happening in this system when you put these two guys together, how the spin relax? So there are two scenarios. So one is when you have intra-Waalais scattering, so it means that the spins are living only in one of the valleys. So if they are living in only in one of the valleys, what they show is that you should measure spin lifetime, spin lifetime anisotropy at this 1/2. And this is because the spin relaxation is driven by Rashba spin coupling. So in order to observe this strong anisotropic dynamics, you have to introduce inter-valley scattering. So in this case, the spins are flipping from one valley to another, and they see different spin orbit fields when they are here in this valley or when they are here. So they have spin orbit fields in one direction or in another one. So it makes that when they are flipping from one valley to another, they are relaxing through the Diakonov-Perel mechanism. So what we can do more with these devices, so is these experiments based on spin to charge interconversion. So very briefly, there are two main mechanisms for converting charge into spin and spin into charge. So one is the spin Hall effect. So this is, everyone knows, so if you run a current through a high spin orbit coupling material, you can generate an a transversal spin current with the spins pointing out of plane. But you have a second mechanism here, but this the spin galvanic effect. So if you remember what I explained previously, so here we have an in-plane spin texture in the structure of graphene. So if now I run a current in this direction, I will shift these guys and I will create a spin density in plane in a direction that is transversal to the electric field. So this is basically the scheme that of the device. So here what we attach metal electrodes in graphene, and graphene here is again partially covered with the transition metal dicogonite. It is tungsten disulfide, the results that I will show you here also. And then we run the current through the graphene. So in principle, you have these two effects. You have spin with spin polarization out of plane that are arising from the spin Hall effect, but you also have this spin density that is coming from the spin galvanic effect. Another question is how we detect this. Again, we use spin-sensitive contacts here, and how we can disentangle and how we can know if the spins that we're detecting are coming from the spin Hall effect or are coming from the spin galvanic effect. It is obviously playing with the geometry of your magnetic field. So if you apply magnetic fields that are, you apply an out-of-plane magnetic field, so the spins that arise from the spin Hall effect do not precess, and you will be only sensitive to the to the non-equilibrium spin density that are coming from the spin galvanic effect. And just opposite, so you apply the magnetic field along the spin, this direction, the spins that will experience the precession will be only the ones that are coming from the spin Hall effect. So now there is a key aspect on this. This is very technical, but this is essential. So if you want to really control that you have these effects in graphene, you have to be sure that there is no current shunting through the transition metal dicogonite. Otherwise, you can have, in the bulk of this transition metal dicogonite, you can have spin Hall effects and you can have spin polarization. So this is what we did before. So in our device, so unfortunately this picture didn't show you a real device. Now you have to believe me. So we attach here also metal electrodes on the transition metal decay cabinets to characterize this by itself. And what we did is we inject a current, we apply a voltage through this interface, and we measure what was the current that was flowing from the TMD to the graphene. Okay? So these are the IV characteristics that we measure. So you see that here we are in the band gap of the TMD, and then it starts to conduct electricity for this gate. So we did this as a function of the electrostatic gating in the system. So with this electrostatic gating, I didn't mention before, so we are able to control the carrier density in the system. Okay? So by playing with this, we can know when this TMD starts to conduct. And here you have so how is the characteristics of graphene. So you see that the charge neutrality point is at this gate voltage around 15, and fortunately we were in the region in which the TMD is not conducting. So we were able to measure these effects to just to be sure that we're not current flowing through the TMD, and also we were able to distinguish how the system behaves if you have holes or electrons. So this is again, so in this case we apply the magnetic field in plane. So this is the precession of the spins that are coming from the spin Hall effect. You see this oscillatory signal. This is a clear indication that you have the precession and you are sensitive to this. And this is the same in the case of magnetic field out of plane. So this is then the signal that we are detecting is coming from the spin galvanic effect. So dots are experimental points. Lines are fittings in which we consider a single free parameter, that is the spin Hall angle or the spin galvanic effect. Okay? And these are the figured merits that we have. So you see that we can, in these systems, if you're pretty sure that the effect is occurring in graphene, you can improve the figured merits significantly. Okay, so we did the same for as a function of the gate. So we saw how the spin galvanic effect change sign, and this is just because this is directly proportional to the carriers that you have. So depending if you have holes or electrons, you change sign. But we measured this signal for the spin Hall effect, and we were a bit puzzled because it is also to expect here to see this change with different magnitude for electrons and holes, for some very technical detail of the band structure of the system, but we were puzzled. So why we are not distinguishing this change? Okay, so we introduced another energy in the system that was temperature. So we realized the same experiments at different temperature, and then at some point you see we start to observe clearly this peak and dip. Okay, so the problem here at room temperature was that so we have electron hole bubbles, and so temperature fluctuations that basically blur the signal. But if you are able to reduce this energy, so you see that we can distinguish, and so we were very confident with these results. So indeed, there was some calculations from the Stefan Roche group that they observe and they extract exactly the same behavior. From this, we can estimate what are the spin orbit coupling that you have in the system. And we simultaneously measure the spin signal on the right electrode and on the left electrode. Exactly. And then we apply again, so we measure for different magnetic field configuration. So
the important thing is that you have the two magnets, so then you can see.
Exactly. So you have to measure at both sides, having a spin sensitive in both sides, and then by playing also with the geometry of the magnetic field, you can disentangle all the spin components that you have in the system.
for